Okay, we're looking at kinematics topic 3 here. So the first thing we're going to look at is, first thing here is your notes should look very similar to these notes, okay? So don't be lazy in what you do with this topic. It's a very hard topic, and it's important you write out in full. So first thing we're looking at here is displacement. What's the definition of displacement? Well, graphically we're looking at a straight line distance between 2 points, okay? It's always a straight line distance, and it's a distance with a direction, okay? So look it up in the wiki. You'll find it in the dictionary on the in our Year 12 wiki site. So an example of it, though, is a car journeys from X to Y. He follows a curved path, okay? His distance is the one that just keeps counting as you go along. It's like this odometer on your car that measures distance. In this case, it's 12 kilometers. However, if we're looking at displacement, it's the straight line distance, okay, between the 2 points, so that's 6 kilometers, and the angle, okay, so the angle is 25 degrees south of west. Okay. Now speed is related to distance, okay, so we're going to define it by the word equation. Speed equals distance over time, okay. It is a scalar, it's not a vector, okay. And so putting it into the equation, V equals D over T. Unit, ms to -1. So we've done that one before. The next one, though, which we're going to look at here, is average speed, which you would have seen before. Just remember it's total distance over total time. Velocity is a little bit different, okay? It's defined by the word equation, velocity. Now we can't use distance here. It is displacement, because velocity depends on direction, so we use displacement because that depends on the direction. So velocity is scalar or vector. It's not scalar, it is a vector. Units, V equals S over T. Oh, sorry, not units, formula. Unit is ms to -1. So if we've got an example here of this plane flying around in the circle here, okay, at all times the speedo, so you've got your speedo on the plane, okay, doesn't really look like this, okay, that speedo is pointing at 200 kilometers an hour, okay, and it doesn't change for the whole loop. So over here, it's still got the same speed vector there, or sorry, speed in that direction. Now, when you look at this, the plane has changed its direction from, let's say, north in this case to south, but it's keeping the same value of 200 kilometers an hour. So that means the speed is unchanged. Okay. However, velocity does change. So that means, because velocity changes, we'll see later, change in velocity means there must be some sort of acceleration. And if you remember last year, if you have an acceleration, then you must have a force. Okay, so in this case, to provide this acceleration, there must also be a force. That's evidenced in the plane by the plane will have to bank and use some of its lift force to make it go around in the circle. Okay, so looking at some graphs here, we've got displacement versus time. In this case, if I put a value here of, let's say, 3, the value doesn't change over time, so that means the displacement must be constant, so it must be stopped. Okay, or stationary. This one here, if I split this up into equal values of time, then the change in displacement for each of those times is the same. So that's the same as that. So each of these changes in displacement are in the same amount of time. So this is a constant positive velocity. Okay, why is it positive? Because the gradient's positive. Which one's largest? One is the largest velocity. So looking at this one here, we could take the 0 as a reference point. So there's my reference point 0. There's a positive side, negative side, and so what we're happening here is actually we're traveling from the positive side to the negative side as we go along. So if we take this side here as positive, that negative, our object, okay, so our triangle, not triangle, bucket, is going to travel this way, okay, at a constant rate. So this is constant negative velocity. So all we're saying here is, I mean, you could have just had the graph go to there. We could have said that the object is only traveling back to the start again, okay, at a constant rate, so it's constant negative velocity. But you could actually also just then travel past that starting point. Well, the next one here, you got to think about it here: positive, negative side, so distance. Okay, so one's to the left or one's to the right. So what we're doing here is we're starting on, so this is our 0 reference, we're starting on the negative side here, okay, and we're starting off at a sort of a slow rate, and we're actually accelerating. So we're going slow, and then suddenly we accelerate off in the positive direction, okay. So this is acceleration. It is positive, okay, because it's getting the positive values larger. This one here, you can think about it, the change in displacement for that amount of time is quite large, okay. For that same amount of time over here, there is a small change in displacement. So this one must be slowing down. And you can see here is that we're going from the negative side to the positive side. So 0 reference, we are starting about here, and we're going fast and then slowing down, okay, until it's almost stopped. Okay, so this is essentially deceleration. This one over here is deceleration as well, but we're going in an opposite direction. You can tell it's deceleration by there's a big change of displacement in the unit of time there, and then there with the same amount of time, much smaller change in displacement. So we're slowing down, and with this time we are heading towards the negative side. So we're going fast this way, down to slow that way. Now, the gradient value, if you look at it, what do we put on the y value? We had displacement on the y value, and we had time on the x, okay? So if I put them in there, what's the y value on top here? Change in y was s, divide that by time, s over t equals v. So the gradient of a displacement time graph is velocity. And we saw that. We actually talked about it. We talked about the slope of it. It meant that one was going faster than the other one. Now, here we have an example. So let's just flick to the question. First one, what's the displacement at 1 and after 6 seconds? So, at 1 second, the displacement is 10 meters. What's the displacement at 6? Okay, it is essentially 20 meters. Okay, sorry, negative 20 meters. Well, that looks like 120. Sorry, 20. What's the final displacement? Where do we end up? We end up back at 0. What's the total distance traveled? Well, this is a bit different. So our displacement is 0 because we're back to our original position, but we have actually traveled 20 meters there, 20 meters back, and then 20 meters this way, and then 20 meters back. So what is our total distance traveled? It's going to be 80 meters. What's the velocity at time equal 1 second? Well, that's just the gradient of this line there, okay, because that's the gradient through that 1 second. So it's going to be 20 divided by 2, which makes 10. Okay, so that would just be 10. I expect you to do some working. What's the velocity at 4? Okay, so 4, that point there, it's not 0 because it's on 0. It's the gradient along there. Okay, So there's a big change. There's actually a 40 change in 2 seconds. So that's going to be negative 20. What's the velocity at 6 seconds? That's 0. Okay, it's not moving anywhere. What's the average speed? Well, that's the total distance divided by the total time. Total distance is 80 divided by, how long are we going for? 8 seconds. Okay, so 80 divided by 8. Okay, so that makes 10. So 10 meters per second is your average speed. However, what's your average velocity? It's actually 0 as your total displacement. So we've got 0 meters per second. In other words, you don't actually have to be moving anywhere to get the same displacement. In other words, end up at the same place. Looking at some velocity time graphs. In this case here, if we put a 0 there, unchanging, so 0 velocity means you're stopped. Okay. And this one here, if we put in a value, let's say 2, we're going at a constant velocity of a certain value, okay, unchanging. This one here, now we've got to think here you go 0, negative, positive. As we go down this way, you're actually increasing your negative value. So this graph here, because it's going this way, we are decreasing our negative velocity, but then we are increasing our positive velocity. Okay, so what you think about this is let's have negative as left, and let's have positive as right. So what's happening here is we are going left but slowing down. So here's my thing. I'm going left but slowing down, and then I'm turning around and speeding up to the right. Okay. Now, one way of saying is this is constant positive acceleration. And in this case here, the positive acceleration works to decrease a negative velocity and increase a positive velocity. Okay, so if you think about this one over here, this is positive, 0, negative. This must be a constant negative acceleration. So this works to decrease a positive, the opposite, and increase a negative. So this is essentially just like a ball getting thrown up in the air and coming down, where, as it's going up, it's decreasing in the positive direction, which we'll say is up. Okay, so it's decreasing its velocity in the positive direction as it's going up, and then as it reaches the top, it then starts increasing its velocity back down again. And at all times, it's a straight line because the acceleration is equal to negative 9.81 ms to negative 2. This one here, we are changing our rate of acceleration, so we're increasing our positive acceleration. Okay, so increasing positive acceleration. This one here is a decreasing positive acceleration. Okay, so remember, still got the negatives and positives here. We're decreasing the negative value there, but we're increasing our positive. So we're still accelerating for the positive end and decelerating for the negative, but it's always a positive acceleration. So my advice is never to use now deceleration, acceleration. Use positive or negative acceleration. So if you think about this one here, positive side to the negative side, okay, direction. So this one here, we're slowing down in the positive direction, and then we're speeding up in the negative direction. But the rate of change of that velocity is getting larger. Okay, so there's not much of a change in velocity up here. Okay, there's a big change in velocity down there. This one here, their rate of change is quite high here, and it's getting less here. So our rate of acceleration, in this case negative acceleration, is getting less. So what do the gradients of these lines mean? Okay, so remember on the y-axis was velocity, on the x-axis was time, so v over t is equal to acceleration. Okay, what's the area equal to? So that's the, if you have a think about this line here, let's say you're going at a constant velocity. The area under this line here, you calculate it by doing v times t, and that happens to be equal to s, displacement. So looking at this example here, we'll just quickly go through it. So what's the velocity of 1, 3.5, and 5? Okay, so 1, what's the velocity? It's 5. Just read it off there. 3.5, 20. And at 5, 0. Okay. What's the acceleration at 1, 2.5, 3.5, and 5? So 1, you find that gradient. So it's going to be 10 divided by 2, so it's 5. What was it? 1, 2.5, 3.5. So 2.5 there, greater acceleration, okay? So this time is going to be a change in 10 and 1, so it's 10. So from 5 to 10. There, flat, 0, and then at 5 is the gradient down that way. So you could say that it's we've done 20 in 1 there, so it's negative 20 meters per second. The distance traveled in 5 and the distance traveled in 10. So to find these, it's the total area under the graph. So in 5, you can just split it into triangles like this, square there, triangle there, and so on. Okay, and another square there, and you can work out the total value. And then if you're going to work it out for 10, you add it. Okay, so you get the total distance covered. Okay. For displacement though, what's the displacement after 10 seconds? It's 0. Okay, you've actually gone, displacement after 10 seconds is not 0, that's the velocity at the end. To find the displacement, you get the positive displacement and you add it to the negative. So it'll be like positive value plus a negative value, okay? And so the difference between these two areas, the one at the top there and the area at the bottom, will give you your displacement. And so the average speed is your distance over time, and the velocity is the average displacement over time. So it's quite interesting. You could have a average velocity of 0 required for this one as well. Now we can explain a lot of the kinematic stuff with equations of motion. Okay, so there are 4 equations of motion, and let's go through the derivatives now. So A equals change in v over t. Okay, so that's your defining formula for acceleration. Okay, and if we put in some letters here, v minus u over t, where v is final velocity minus the initial velocity u divided by time. Rearrange it, I get v equals u plus at. That's equation number 1. If we had a graph of uniform acceleration like this one here, how will we calculate the average velocity? Well, you'll get the starting velocity and the final velocity, add the two together, and divide it by 2. So let's substitute it into this equation, s equals vt, so u plus v over 2 for that average velocity times time. That's equation number 2. Now the next step is, we've got these two equations here, v equals u plus at, and we've got s equals u plus v over 2t. Now if I substitute this expression for v into this one, if I substitute that one into that one, then I can have s equals u plus at over 2 times t. So there's that u plus at in there. Okay, and I've substituted in for v. So simplifying this, we can have s equals 2u over 2 plus at over 2 multiplied by t. And then I can simplify that again. I get ut. This is if I multiply the t out. Okay, multiply all that in there. I get ut, the 2's cancel, plus half at squared. That's equation number 3. Now the last one here, what are we missing? We're missing one with v U, A, and S. Okay, so let's look at that one. So, two equations again, V equals U plus AT, and I'm going to rearrange that for T equals V minus U over A. And another equation we've got is S equals U plus V over 2T. Okay, now if we substitute this T expression into here, you get S equals U plus V over 2 times V minus U over A. If I multiply each side by 2 and A, I get 2AS equals U plus V times V minus U. If you multiply that out, you get 2AS equals V squared minus U squared. And then rearranging, you get V squared equals U squared plus 2AS. And that's equation number 4. So for example, a car moving initially at 3.5 meters per second accelerates at 2 meters per second for 5 seconds. What is the car's final velocity? So we're looking at this thing here. We've got U, initial velocity, A, acceleration, time is 5. So what's the final velocity, V? So we've got V, U, A, and T. I'll use the equation V equals U plus AT. Substituting in the values, 3.5 plus 2 times 5. So that makes 13.5 meters per second. B, how far does it travel while it is accelerating? So now we're trying to find S. Okay, so S, A, U, and T. Okay, so what equation can we use here? Let's have a S equals UT plus half AT squared. So let's put them in. U is 3.5, so it's 3.5 times 5 plus half times 2 times 5 squared. Okay, so if we put all this in, and we get 42.5 meters. That's essentially just talking about what we did. So, still working, but to check. Okay, 13.5, 42.5. The ball is thrown vertically into the air. Is left the thrower's hand at 3 meters per second. How long will it take to reach its maximum height? Okay, so I have room to answer. Yes. So for A, what do I need to find? Well, if you look at this question, look at this ball here, and look at it there. At the very top, V is equal to 0. At the very top, it's got no velocity. But down here, U is 3 meters per second. That's how fast it was going before it left the hand. Now, something with all these questions to do with flight, you have to remember that you have gravity, okay, the gravitational acceleration. So if we look at the question here, we have got A, okay, negative 9.81. We've got V, which is 0. Okay, we've got U, which is 3. Okay, and we're trying to find time. Okay, so how long will it take? So that's time. Okay, so we're trying to find T. So what equation has V, U, and A and T? So let's think about that one. Has everyone got it? Hope you all got it. Okay. So we're just going to do V equals U plus AT. Okay, so in this case it's going to be, what's your initial? Final is 0, 3 plus negative 9.81 T. So let's put the 3 to the other side. So 0 minus 3, so negative 3 equals negative 9.81 T. And so T is equal to negative 3 divided by negative 9.81. Okay, so it's about 0.31 seconds. Okay, you notice that those negatives cancels out. So you need to be aware that they should do cancel out. Just calculate going up, so now what's going down? Okay, so let's go look at the question. Question is, how long will it be in the air for? Okay, it's actually going to be 0.31 times 2. Okay, so it's going to be equal to 0.62 seconds. Same time up as it is going to be coming down. List what you've found and what you need. Be careful to choose the right time. So what we're looking for here is how high will the ball go? If we're going to use time, we have to only use half the flight, okay, because it's from here up to the maximum. So we know V equals 0, U equals 3, A equals negative 9.81. We also know time equals 0.31 seconds. So we can actually use any equation to find S. Let's use S equals U plus V over 2T. You could use, one that I would recommend using is S equals UT plus half AT squared, or you could actually use V squared equals U squared plus 2AS. Actually, maybe we use that one because we're not using a calculated value. So 0 is equal to 3 squared plus 2 times negative 9.81 times S. So 3 squared, 9. Negative 9 on this side, okay, is equal to negative 19.62 times S. So S equals 0.46 meters. Hopefully that's right. So, if you want to find out what G actually is, all you need to do is you could drop a ball, in this case, you can measure the time, and you can measure the distance that's covered. Okay, so S and T are the two things we can measure. So if we drop a ball 5 times from different heights, we're going to do this in class. And then, so remember, for the two variables you've chosen, what are they? S and T. Okay, we're going to put them into a table. We're going to graph S versus T squared. We're going to use the gradient and a kinematic equation to find G. What's the kinematic equation? S equals half GT squared. Where did that come from? S equals UT plus half AT squared, and U is 0 because we're starting from rest. This is a good device, this one here. This is one that you need to understand how it works, so we'll show you in class, but this is a picture of it for your notes. The next thing we're going to look at is projectile motion. Now, in a vertical direction, okay, everything accelerates downwards at 9.81. Okay, if it was going up, if this ball was heading up in the upwards direction, it would still be accelerating downwards. It would still have an acceleration opposing its motion. If we looked horizontally and we ignored friction, objects would travel at a constant velocity. Okay. Now, if we combine the two, let's look where each of these points are going to be. Okay. So that's where each of these things are going to be. You get a curve like this, and that's called projectile motion. Oops. Sorry about that. Wrong button. So, if you look at it here, the sum of these two components makes this one here. So that component, so this component here to that component there gives you that vector there. Okay. So when we add the up and down, this is what it goes like. So the horizontal component of each of these, that one, that one, that one, that one, that one, that one, they're all constant. However, the vertical component gets smaller on the way up because the acceleration is against its motion, and then it increases on the way down. So this makes it quite tricky. Here's more pictures of it. Here. More pictures. Now, when you're answering questions, you've got to think of the components. Vertical is changed by acceleration g, and the horizontal is constant. So you need to find the time and height with the vertical component, and then the distance covered horizontally is based upon the time of flight. So you find the time from the vertical, and then using that, you can then find the horizontal distance. So, Billy hit a cricket ball with an initial velocity of 48 meters per second and an angle of 30 degrees to the horizontal, ignoring air resistance. calculate the vertical and horizontal components of the velocity. So all you got to do there is, we'll do this one in class, but you think about, there's your vector there, that's 48 meters per second. Okay, it's at an angle of 30 degrees. So all you do is to find the vertical component, okay, is going to be 48 times sine 30. And then the horizontal equals 48 times cos 30. Okay, the time it takes to reach the maximum of elevation. Well, in this one here, we're going from a certain u value, which is equal to, what's the vertical component? It's 48 times sine times 30. That's the initial vertical component, and we get to a v equals 0 at the top. Acceleration equals negative 9.81, and we're trying to find time. Okay, so it's using a kinematic equation of v, u, a, and t. So in this case, it's going to be v equals u plus at. The total time of flight was 2 times your answer in A. How far will the ball travel? Well, if we know how long it's in the air, okay, so let's say time is a certain value, then we can just use s equals vt, because it's a constant velocity, and we know the time is in the air, we know how far horizontally it's going to go. And it's a similar question here.